All right, we can now move on. We are now going to talk about improper things. So, what does it mean for something to be improper? So, I'm going to write it out here because I'm realizing it's not on my note sheet. So, I'm just going to write it really quick. An improper integral, that is an integral that is not continuous over the bounds or has a bound that cannot be plugged in. So there are several ways these can look, and I'm going to use my note sheet to kind of show kind of what I mean here. Okay, so looking at example number one down here, my bounds are going from 1 to infinity. Well, that's not a number I can plug in. So that's why this one counts. Same thing with example number 2. Infinity is not a number I can plug in, and so that's why that counts. Same thing here. Negative infinity there, negative and positive infinity there. Looking on page 2 at example number 5, my region is going from 0 to 4, which seems okay, but then think about if I plugged in a 4 here, 4 minus 4 would give me 0 in the denominator, which I can't have, so that's why this one counts. Example number 6 goes from 0 to 2. Well, the natural log of 0 isn't a real thing, and so that's why this one counts. This one, at first glance, looks like it may actually work, but negative 1 to 1 includes the point 0. 0 cannot be plugged in there, so that's why that one counts. So basically speaking, how I'm going to work these is I'm going to then replace whatever I can't do with a t, and then I'm going to do the limit as t goes to that thing. So for example, if I was doing like the integral from 1 to infinity of a function, and that's not a number I can plug in, right? So I'm going to replace it with a t and do the limit as t goes to infinity and replace it with a t. Then I'm going to work this out and then find the limit as t goes to that thing. Another thing I can do is I can split it up. So if I had like the integral negative infinity to infinity, I can split this up and pick any point between them. So let's just do 0, but it doesn't matter. 0, and then add 0 to infinity, and I can split it up like that. Then I can do this same rule here to both of those. So this would be the limit as t goes to negative infinity of the integral from t to 0, plus the limit as t goes to infinity, integral 0 to t f of x dx, and work them out. That's how I'm going to handle these. So let's look at example number 1. Example number 1, determine whether the area between the graph of f of x equals 1 over x and the x axis over from 1 to infinity is finite or infinite. So remember, we learned this in Cal 1 and then at the very start of Cal 2. Area under a curve is integral from a to b of f of x dx. So I'm going to use that. So here, area is going to be equal to integral. The region is right here, 1 to positive infinity. And my function f of x is 1 over x. So once again, this is a number I can't plug in, so I'm going to replace it with a t and do the limit as t approaches that. And that's okay because this is now something I can do. The integral of 1 over x, we've done this a few times, is the natural log. So this is the limit as t goes to infinity of the natural log of the absolute value of x going from 1 to t. So plug in our top bound first, which is t. So this is the natural log. We know t is positive because it's greater than the 1. So I can just do this, the natural log of t minus the natural log of my bottom bound, which is 1. Well, the natural log of 1 is 0. So this is just the limit as t goes to infinity of the natural log of t. Well, one thing I know about the natural log is it just goes up and up and up for all time. So this is going to be equal to infinity. So that means this area is infinite, which also means that it diverges. You are going to hear me use this word a lot in Cal 2. Diverges means it's just going to grow and grow for all time. Remember, if that doesn't make sense, please let me know. Let's move on to example number 2. Example number 2, find the volume of the solid obtained by revolving the region bounded by the graph of f of x equals 1 over x and the x from 1 to infinity about the x. So I'm looking for the volume, which means I've got to know, am I going to use the disk or am I going to use the shell, right? Well, this is a function of x rotating around the x, which means I want to use the disk, right? So remember that the disk method for volume equals pi integral from a to b of my function squared. So I'm using that here. So the volume is going to be equal to pi integral. My region is from 1 to infinity. And my function is 1 over x. 1 over x squared is just 1 over x squared, which is like saying, oh, and then also remember here, this isn't something I can plug in. So do the limit as t approaches it, and then replace it with a t. But again, 1 over x squared is 1 over x squared, which is like saying x to the negative 2. Okay, so now take the antiderivative of that. Remember, I'm going to add 1, which would give me the negative 1. Divide by my new power gives me negative x to the negative 1 from 1 to t. Plug in a t. X to the negative 1 is like saying 1 over x. So this is going to be negative 1 over t. Minus would make it plus 1 over a 1. 1 over 1 is just 1. So now do the limit as t gets really big of 1 over t. Well, 1 over something really big is going to be really small. So this limit is 0, which just leaves me with pi times 1, which is pi. So this converges to pi because I got a number. The volume of this is pi. Now, you may be thinking, how does it make sense to have a number there? Because if it's infinity, it's just going to keep going and going forever and ever and ever and ever and ever. So how does it make sense to actually stop at pi, right? Well, the reason is because as I grow and grow and grow and grow, bigger, 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 the amount of space there is getting smaller. So think about the graph of 1 over x, right? The graph of 1 over x looks like this. And I'm going from 1 to infinity, which means I'm starting like right here. the amount of space in here is getting smaller and smaller and smaller and smaller and smaller, 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 smaller. So as I go on, these little smaller bits over here aren't going to really add much. So basically, it's going to stall at pi, is what it means. Example number 3, evaluate the integral from negative infinity to 0 of 1 over x squared plus 4. Integral from negative infinity to 0 of 1 over x squared plus 4 dx. Okay, so once again, this isn't a number I can plug in, so I'm going to replace it with t and do the limit. Negative infinity, integral from t to 0, 1 over x squared plus 4 dx. So now I just got to worry about this. The derivative here, notice this looks a lot like inverse tangent. Remember, we learned that the derivative of inverse tangent is 1 over x squared plus 1. The difference here is that I have a 4 when I really only want a 1. So then I've got to make this a 1 by factoring out a 4. So this is going to become limit as t goes to negative infinity, infinity, t to 0. Once again, I want this just to be something squared plus 1. So factor out a 4 gives me 4 times x squared over 4 plus 1 dx. Now, since I have a 4 in the denominator, I can bring out a 1/4 limit. I forgot the limit. One over, and then again, I want this to be something squared. Well, I must have squared x over 2 to get x squared over 4 dx. Now I can use u substitution. U has to be x over 2, which means the du has to be 1/2. So I need a 1/2 up here. In order to have a 1/2 up top, I need to times it out front by a 2. 2 times 1/4 is 1/2. Limit as t goes to negative infinity of, plug both of these into the u, so this would be t over 2. 0 over 2 is still 0, of 1 over u squared plus 1 du. Now I know that is inverse tangent. Limit, I keep forgetting the limit. Don't forget the limit. Of inverse tangent of u from t over 2 to 0. So that's going to be 1/2. Plug in my top bound first. My top bound is 0 minus, plug in the bottom bound. And now from the unit circle, we note that the inverse tangent of 0 is 0. This has a t in it. So as t goes to negative infinity, t over 2 is also going to go to negative infinity. And knowing what I know about inverse tangent, remember the graph of inverse tangent, we know this from trig or pre-cal or whatever. Graph of inverse tangent looks like this, where it goes from negative pi over 2 to pi over 2. So as it gets really small, it's going to negative pi over 2. So this becomes 1/2. This is going to be negative. The limit is negative pi over 2. The negatives are going to cancel out. 1/2 times pi over 2 is pi over 4. So this means it converges to pi over 4. If any of that trig stuff doesn't make sense, let me know. I will be happy to help you out. It's really helpful to know a lot of trig, is the point there. Okay, example number 4. we're going to do the integral from negative infinity to positive infinity of x e to the x dx. So inside of here, I have a product. We now know that for a product, I've got to do this by parts, okay? We also learned that whenever I do things by parts, we did this in section 3.1, that it's helpful to ignore the bounds until I get it done, right? So let's do that. Let's ignore the bounds for now and then use them at the very end, okay? So ignoring the bounds for now, remember by parts, I want to identify a u and a dv. Let's use x for the u because then du is just 1 dx, which means I broke it down, which is what I want to do, which would mean dv would be e to the x dx. The antiderivative of e is just e. So this is going to become u times v minus the integral v du, and the integral of e is just e. So this is going to be x e to the x minus e to the x. I would normally do plus c, but since I have the bounds, I'm not going to. So now keeping in mind my bounds, neither one of these are things I can plug in. So I want to split it up, okay? So I'm going to do the integral from negative infinity to, I can pick whatever point I want to. 0 is just easy to work with. And then add, start at 0 and go on. Neither one of those I can plug in, so we're going to do the limits for both of them, replacing it with t. We already did the derivative, so let's plug those in. T to 0 plus the limit as t goes to infinity of x e to the x minus e to the x from 0 to t. Plugging in my top bound first. Plugging in a 0 here would make it 0. E to the 0 is just a 1, so that's going to become negative 1. Then minus, plug in a t, so t e to the t. Minus makes it plus e to the t. Same thing over here. Plug in my top bound first, t e to the t minus e to the t. Plugging in a 0 here would make it 0, so don't even need it. Minus would make it plus, e to the 0 is 1. Let's continue working this out. As t goes to negative infinity. So the negative 1 is just the negative 1, right? The limit for the negative 1 is just negative 1. Minus the limit as t goes to negative infinity of this round. So what that is going to do, that's going to put a negative infinity here and a negative infinity here, right? So a negative infinity in the power, what that is going to be like is as if it was like e to the negative infinity, right? Whenever I plug it in up here. So what that's actually going to do is make it like 1 over e to the infinity, which is really big, right? This is really big. 1 over something really big is really small. So this term is going to go to 0. Same thing with this one right here. Same idea, it's going to go to 0. But what's going to happen over here, it's going to make this get really big, right? Because as t gets really big, this whole term is going to get really big. So I can go ahead and even just stop right there because I know this whole thing, it doesn't even matter what anything else is going to go to infinity, which means it diverges. Okay, so now we can move on to if I have some numbers that don't work out very nicely. So example number 5. For example, example number 5 is the integral from 0 to 4 of 1 over the square root of 4 minus x dx. So the problem here is that I can't plug in a 4. So once again, replace it with a t. Limit as t goes to 4 of the integral 0 to t. 1 over the square root of 4 minus x is like saying 4 minus x to the negative 1/2. Okay, well, I know how to handle this if it's just something to a power, right? But since I have some stuff in there, I've got to use u substitution. U is going to be the 4 minus x, so du is going to be negative 1 dx. So this is going to become negative, limit as t approaches 4, of the integral. Plug 0 into here, 4 minus 0 is 0. Oh, no, it is not. 4 minus 0 is 4. Plug in a t, and that's 4 minus t of u to the negative 1/2 du. So our rule here, add 1 to the power. Adding 1 to the power makes it 1/2. Divide by that 1/2 is like saying times 2. So this is 2 times u to the 1/2 that I'm going to do from 4 to 4 minus t. Plug in our top bound. We can pull this 2 out front to make it negative 2. Limit as t goes to 4 of. That's going to be 4 minus t to the 1/2. That's like saying the square root of 4 minus t minus, plug in a 4, square root of 4. That's going to be negative 2. The limit as t goes to 4. Plug in a 4 right there. 4 minus 4 is 0. Square root of 0 is 0. Minus the square root of 4. Square root of 4 is 2. 0 minus 2 is negative 2. Negative 2 times the negative 2 is 4. So this converges to 4. It's not as hard whenever it's just a number because you can, for the most part, most times, you could just plug it in and get it. Example number 6. Is going to be the integral from 0 to 2 of x ln x dx. So again, this is a product, which means I've got to do it by parts. Whenever I do things by parts, I am going to ignore the bounds, right? So for now, pretend like they are not even there. So we need to pick a u and a dv. Remember, we talked about this, that whenever I have the natural log of x, I can't take the antiderivative of that. So the natural log always has to be my u. So du is 1 over x dx. That means dv has to be an x. The antiderivative of that is 1/2 x squared. So this is going to become uv, uv, so 1/2 x squared ln of x minus the integral v du. So 1/2 x squared times 1 over x is just x. The integral of x is 1/2 x squared, so this becomes 1/4 x squared. Again, normally I would do plus c, but since I'm going to plug in bounds, I don't have to. Okay, so what's the problem here? 0 can't be plugged in, right? So I've got to replace it with t and do the limit as t goes to 0 of t to 2 x ln x dx. I already know what the antiderivative is. T to 2, plug in my top bound first. me 1/2 times 2 squared times the natural log of 2 minus 1/4 2 squared, and then minus plug in a t. So that's going to be 1/2 t squared natural log of t minus makes it plus 1/4 t squared. So work this out. 2 squared is 4. 1/2 times 4 is 2 times the natural log of 2. Minus 2 squared is 4. 1/4 times 4 is 1. So minus 1. Limit as t goes to 0 of this stuff. So as t goes to 0 here, that's going to be 0 squared. So this whole thing's going to be 0. Plus 0 squared over 4 is just 0. So you end up with 2 ln of 2 minus 1. One more example that's like this. Example number 7. Integral from -1 to 1 of 1 over x cubed dx. So let's think about what's wrong here, right? I talked about this a little bit at the start, but notice that in between here, we have x equals 0, right? Well, 0 can't be plugged in here. So that's what's wrong here, okay? Again, 0 is between these, and 0 can't be plugged in. So that is what's wrong here. So I'm going to have to split it up. 0 is where I'm not happy, so I'm going to do -1 to 0. This is like saying x to the -3rd, so let's rewrite it like such. And then do it again from 0 to 1. Because by splitting it up like that, now I can use my whole t thing, right? So this is going to be the limit as t goes to 0 of the integral of -1 to t x to the -3rd dx plus the limit as t goes to 0 integral from t to 1 x to the -3rd dx, and work it out like that. So this is going to be the limit as t goes to 0. Add 1 gives me a -2. Dividing by that gives me negative x squared. Nope. X to the -2 over 2. The minus sign out here is where that went to. From -1 to t plus limit as t goes to 0. Same thing over here. Again, add 1 gives me -2. Dividing by that gives me negative x to the -2 over -2. Oh, the -2, the negative's already up there. From t to 1. Play on our top bound first. Limit as t goes to 0 of negative t to the -2 is like saying 1 over t squared. So 1 over 2t squared minus makes it a plus. -1 to the -2, that's like saying 1 over -1 squared, which is just 1. So this just becomes 1/2. Plus the limit as t goes to 0. Plug in a 1, the same thing happens. That's just 1, so -1/2. Minus makes it plus, plug in a t. T goes to 0 here. So as the denominator gets really close to 0, the whole thing is going to get really big. So think about if I plugged in like 0.01 inside of here, right? The denominator is going to be really small, which makes the entire thing really big. So this is going to go to infinity, which tells me I can just go ahead and stop. This is going to diverge. Once again, 0 in the denominator makes the denominator really small, which makes the whole thing really big. So it's going to diverge. Of course, if any of that doesn't make sense, please let me know. All right, the last part here of this section is going to be something called a comparison theorem. And what this is going to help us do is if I know something about a function, it can tell me something about some more stuff too. So if I know that the limit of f of x diverges, then if there's a function that's larger, it's going to also diverge. So again, right here, if g of x is the larger one, which is what this says right here, if g of x is the larger one, and I know the smaller one diverges, which means it just grows and grows and grows and grows and grows, then the larger one is going to also just grow and grow and grow, because, I mean, it makes sense, right? So if f of x is like right here, and g of x is the larger one, okay? If f of x diverges and just keeps growing and growing and growing, g of x must also just grow and grow and grow, because it's a larger one. So if the smaller one just grows and grows, the larger one is going to also just grow and grow. On that same note, if I know the larger one converges, then the smaller one must also converge. Because if something that's large eventually stops, then a smaller one will also eventually stop. So this is going to help us do some that may be kind of hard, okay? For example, on example number 8, I want to know something about 1 over x e to the x, right? But the complicated thing about it is that this is going to be really hard to show the proper way, right? Because then I've got to do like by parts, I've got to do all of that. So instead of doing that, why don't I see if there's one that's not very hard I can use, okay? So something that wouldn't be very hard is 1 over e to the x, right? So if this function was just 1 over e to the x, let's do that one instead. So integral 1 to infinity, 1 over e to the x dx. Again, it looks kind of like it, right? But it's not as hard. So what this is going to be, this isn't a number I can plug in, right? So we're going to do the limit 1 to t, and I can write this as e to the negative x dx. The antiderivative of that is going to be negative e to the negative x. So bring the negative out front. E to the negative x from 1 to t. Plug in a t. E to the negative t. And then minus, plug in a 1. As t gets really big right here, e to the negative something that's really big, the minus sign means I can bring it to the bottom, right? And so e to something really big is really big, which means this whole thing is really small. So this is going to go to 0. Negative makes it positive. E to the minus 1 is 1 over e. So 1 over e to the x converges. Now let's see if I can use that. Notice here, 1 over x e to the x. Let's see how that compares to 1 over e to the x. Since I'm going from 1 and then up, right? Whenever I do x times e, that's going to make this larger. So since the denominator is larger, the fraction is going to be smaller. So what this means is I have found a larger one that converges. Therefore, by this rule, the smaller one must also converge. So what I could say is something like, since the integral of 1 to infinity of 1 over e to the x dx converges, and since 1 over e to the x is greater than or equal to 1 over x e to the x, we know the integral from 1 to infinity of 1 over x e to the x also converges by the comparison theorem. That's what I can say here. Let's try that was example number 8. Let's move on to example number 9 and see if we can figure that one out using the same thought. So example number 9 says use the comparison theorem to show that the integral from 1 to infinity of 1 over x to the p diverges for all p that is less than 1. So something we have already shown, it was actually example number 1. Example 1. what we showed on example number 1 is that the integral from 1 to infinity of 1 over x dx diverges. Go back and rewatch that one to show why, right? We have already found that. So if I look 1 over x to the p for a p less than a 1, right? How does that compare to 1 over x? Well, if my power is less than a 1, x to the p is going to be smaller than x. So think about it like x to the 1/2, right? That's the square root of x, which is smaller than x, right? So since the denominator is smaller, the whole fraction is greater than. And since the smaller one diverges, the larger one must also diverge. So I would say, since the integral from 1 to infinity of 1 over x dx diverges, and since 1 over x to the p is greater than or equal to 1 over x, we know the integral from 1 to infinity of 1 over x to the p dx also diverges. Again, because I found a smaller one, that also diverges. If any of that doesn't make sense, please let me know.